Okay, start recording. The last time we discussed the power, real power, reactive power, apparent power. And what did we mention about the flow of power? Is there anyone with the suggestion now how the flow, how we have two buses, and we say the buses that we talk about nodes. Okay, nodes. In circuits, we call them nodes. Node, one node, two nodes. In power systems, we call them buses. Okay, so a bus, so a substation, for example, could have more than one bus. Could have two buses or three buses. Mostly two buses. What do we mean by by a bus? Is that the transmission line comes to the substation, for example, 132 kV, and then from 132 kV we step it down to 66 kV, and transmitted to, for example, from Qatar University substation to a Lola. So this is a bus. Where is the bus? The bus at the Qatar University substation, our substation. Another bus could be maybe 400 kV. So it's another voltage. Another voltage we cannot mix with the voltage that's 132 kV. So 400 kV or 66 kV, and we step it down to 11 kV, for example, 66 kV. And we step down to 11 kV. Where do we send it? We send it maybe to the neighborhood, okay, to the neighborhood, the houses close to the universities. So that's 11 kV. So that's another bus. So this substation here could have more than one bus, okay, which is two buses. So but it's only one substation, but would have more than one bus. All right, so the last time we discussed the power. So anyone will tell me now, how do we?
Yes, doctor.
How the power is transferred?
Can I answer, doctor?
Yes, you can answer.
For the real power, for a single bus, it's always from the generation to load. But if we have more than bus, it's from it depends on the voltage angle, and for the reactive power, it depends on the magnitude of the voltage.
In case of what you said?
In case of the reactive power,
we never have one bus, by the way. We always have two buses, sending end, receiving end. At least two buses you will have in the network. That's what you will do in the lab, for example. You will have two buses at least. What we mean by two buses? This is a bus. What you see here, for example, this one here is a bus, and we draw the bus as a straight line, whether horizontal or vertical. Okay, so in this case here, it's written horizontal. So this is a bus. A bus that is sending the, here it is not written, by the way, here it's written, we do not have the, whether we have it here, we do not maybe put the transformer, that's okay. Okay, but it is a bus. So this is from the generation all the way to the load. And this is another bus. Okay, from this bus here, then it goes to the load. And this load could be, of course, a number of houses here, but we don't draw it a number of houses. We don't draw so many. We just draw the total load that leaves the bus, total load that leaves the substation. And then when it leaves the substation, so we calculate, so the meter is at the substation here, and then we call it a load. So always think of the load here. This is the total load that leaves the substation. Where does it go? It goes to the houses or to the industries, different industries. Or it could go only to one industry, for example, big industry. That's okay. Okay, so continue now. What do we mean now by the real power? So how the real power flow if you do this in the lab? In the lab, that's we will do the simulation in the lab. You will be introduced by the by Engineer Sejoy to the power simulator software. And these softwares, they're all similar. So this is the one that they use in Kahrama. They use maybe another company, but it's the same concept, the same thing, that the same input, the same output, and the results and the same decision you take. So when you see the buses, okay. So tell me now what's happening here. So for example, you see this 17.6 megawatt. 17.6 megawatt, of course, just leave the bus here. These red colors here, what you see is the circuit breakers. Okay, but we will not do circuit breakers. This when you do protection, we will talk about the circuit breakers. Okay, circuit breakers is to protect the line. So any fault, for example, higher current than a specified current, the circuit breaker here will close or will open. So it's normally closed for the current to flow. So it's like a fuse, but we don't call it a fuse. Fuse is smaller. We use fuses in the houses. Okay, they used to use fuses. We use fuses in the kettle, for example, that the plug that they use. They use a fuse. Okay, the plug. Don't have it here, but okay. So that's it. We use fuse. Here is the circuit breaker. So if the current is high enough, this circuit breaker here will trip, will open. So no current will flow in here. Okay, so that is in protection course, and the protection course. So it's not, this is beyond the scope of this course. So the course here is the flow of power, how the power flows. Now the power flows, you continue now, the power flows, real power and reactive power. In this case here, what do we mean? 17.6 megawatts. 17.6 megawatts.
For the reactive power, since the voltage is higher.
No, tell me first what's going on here. By just
the losses, there will be losses.
The data. Talk about this system. This is a two-bus system.
Okay.
Talk about it. The generation, the load is, the losses is. This is the way. Okay.
From the generation, it's 17.6 megawatt, and for the reactive power, it's 28.8 mega VAR. Okay, and from megavar. Okay, and it will go to the load, and there will be 16 megawatt losses. No. What is the minus? There will be 1.6 losses, megawatt losses for the power, for the real power, and for the reactive power there will be 12.8.
Okay, so the generation minus the load.
Yes, doctor, but I did not understand this one, the minus 16 megawatt and.
Yes, the minus 16. This is a conventional. This is a generation conventional. So the line, as you are drawing the line like this, or the arrow up, and you draw also the arrow up. Okay, this is only, so don't be confused with this, and it's not necessary. Okay, so this is up the line. This is an arrow. Okay, like this, up. And let me do this again. This is up. And also this is up. Okay. So therefore, because this is not now, the power will flow from the generation to the load. So this arrow is the opposite. So this arrow should go down to be positive. But because we draw the arrow here is up, so therefore we write minus 16. Okay, although the arrow is not. So minus 16, that means this bus here delivers minus 16 megawatt. This bus delivers minus 16. So it absorbs 16. It means that the power flows from bus 1 to bus 2 down, like this. Okay, so the minus 16, do not be confused. The minus 16, it means that this bus gives minus 16. This bus delivers negative 16. Yes, Tamim.
يعني so this means the power loss in the transmission line is the difference between the delivery and the power received in the
Yes.
bus.
Yes.
Mm.
So when you see the losses is the difference between the sending end and the receiving end bus. So when you do a number of buses here, just look at the line, each line there, and look at the sending end and the receiving end, then you can calculate the losses. So the exam, for example, will give you something this, maybe a 9 bus system, and then calculate maybe the losses in transmission line 5, transmission line 6, etc. Therefore, you will look at the sending end and receiving end. Okay, so that's one thing. Okay, so that, and then you calculate all the losses in all transmission line, then will give you the total losses. Okay, when you have a number of buses. So the program will calculate the number of buses, but you need to understand, you can calculate this by hand also to check that your results, okay, to check their computer results. All right, so this is okay. So that's what we discussed, and the reactive power could flow also, as we mentioned, from the load to the generation. So the generator will absorb reactive power. If the reactive power is not absorbed in the transmission line here, if the power is not absorbed in the transmission line and we have excess reactive power, so we're only using real power, and we switch off all ACs, no motors are running. See, only the motors need reactive power. Okay, machines needs reactive power. The air condition because we have they are run. They have motors running, so they need reactive power. So inductive load. So if we don't have inductive load, and we still have a capacitor here giving reactive power, therefore the reactive power will flow the opposite. So you will see the reactive power flowing this way and the real power flowing the other way. When we have excess of reactive power, whether from the underground cables, for example, if this underground cable or transmission line that has capacitive or capacitance, more capacitance than inductance, so the power will flow this way. Where will it go? It will be absorbed in the transmission line here. But if the transmission line still does not absorb, it's more, the capacitance is more than the inductance here. Therefore, it will come to the generator, and the generator has a limit of absorbing reactive power, has a limit. Then what we have is we call it a leading power factor. Then in this case, we call it a leading power factor. When the generator absorbs reactive power, we call it a leading power factor. In other words, if the load is not absorbing, is giving reactive power, is producing reactive power, the load is producing reactive power, is a leading power factor. When the generator is producing reactive power, lagging power factor. Okay, so you need to know the convention between load and generator. Generator absorbing reactive power, the generator will always produce active power, real power. Okay, will not absorb, generator will not absorb real power. Will always either give active power or zero active power. Okay, when we say active means real power. So the generator gives active power, real power. And then when it comes to the reactive power, it either gives or absorbs, delivers or absorbs. So if the generator, you need to write these down, because then that's the way we ask you. If the generator delivers reactive power, gives reactive power, the power factor is lagging. Why lagging? Because if the generator delivers reactive power, it means the load is absorbing reactive power. Of course, where will the reactive power will go? Will go to the load. Okay. If the load is giving reactive power, the load will always absorb active power. Same thing for the generator. The generator delivers. The load will always absorb, will never give real power. The load will never give real power, will never give megawatts. But the load could give megavar, could give megavar. This will go up maybe. How will it go up? If we have capacitors here. If we put a capacitor, high capacitor, and this capacitor here has surplus of reactive power, where does it come, the reactive power? It comes from I square C. Okay, XC. It's like I square X. I square X. I square X gives reactive power. I square X absorbs reactive power. That's I square X. I square C. This is, or XC, not C. XC. Okay, reactive, capacitive reactance. Therefore, if we have a capacitive reactance, here a capacitor, for example, a capacitor. So this is the load. This is part of the load. Capacitor. Then what happened here? This also will give reactive power up to this bus. Either it will be absorbed by the load if it's enough. That's what they do in the industry. They install capacitors in the industry for this reactive power, because we don't want this to be exhausted with reactive power. We don't want too much reactive power from the line, from this transmission line. So what we do in the industry here, because they have heavy motors, large motors. Therefore, they give capacitor here. They put capacitor, so the load absorbs this capacitive reactive. Absorbs the reactive power from this capacitor. Okay. But if this is too much compared to the load, where will the reactive power flow? Will flow to the transmission line. Goes here like this, and then it will be absorbed by the reactance on the transmission line. If still it has not absorbed all together, it will go inside here and the absorption of the generator. We don't want the generator to absorb reactive power. It has a limit. Okay, this is only in certain cases when there's in a lightly loaded condition, the generator will absorb little reactive power. That's okay. Okay. Then the power factor becomes leading power factor, leading. Okay, when we have this case, too much reactive power in the system, leading power factor. All right, so this is the way now. That's, I guess, inshallah, it's clear. Okay, and then what we did here, power factor explained, so you can watch this on YouTube. This is already absorbed within here. And we mentioned about the reactive power, the support. Why do we need reactive power support? It's exactly this way here. As you see the car in here, if you increase this height, this is the reactive power. If you increase this height here, this is the reactive power. So you need more fuel to go up. You need more fuel if you are going with the same speed, for example. You need more fuel to go up. Okay? For the same speed. If you cannot produce more, so you need more fuel. It means more power. You need more power for the car to go up. Why? Because we have this height here is low, is high. So this is a reactive power. The vertical part is reactive power. As you know, what vertical part we talk about? We talk about this triangle here. You remember this triangle here. So this is power, and this is Q, and this is S. This is power. Okay, power. P. Okay, so this is Q. So this is reactive power here. As you can see, you have too much reactive power. And, you need to supply more reactive power, therefore you need to supply also little more fuel like this. It's like this one to be heavy. Huh? We need to reduce the reactive power, otherwise the movement will be what? Will be hard. For this is exactly the same what we talk about. So what's the best way to pull this car? What's the best way? Is a straight line. But if you take it up, you have this angle here. Take it up. You have this angle here. It will be harder for you. So you need to push more. Okay, or to pull. In this case here, you need to pull more because otherwise straight will be convenient, will be easy for the movement. So this is vertical line here is the reactive power. Okay. Okay, so inductive loads, the main loads of industry, of course, the industry is inductive loads, require reactive power. So they require reactive power because they run motors, pumps. For external reactive power support, which is called a compensation. This is the terminology you will use in the lab also. So we need external reactive power. That's what we mentioned about capacitor. But not necessarily, we have a number of compensations there. Okay, capacitor, synchronous condensers. Also, they will give reactive power. So synchronous just produces synchronous condenser or synchronous generator. Not synchronous generator. We call it synchronous condenser. The difference between synchronous condenser and synchronous generator: the synchronous condenser produces only reactive power. It produces only reactive power, Q, no P. Okay, so we need external reactive power. When we have too much of this line, of this height, as you can see, or this height here, to be hard. So we need to compensate this. We need to lower down this one. So what we do, we install capacitors. Okay, we install capacitors external. So we call it compensation, to maintain the system voltage to deliver active power, because we want to deliver active power. Okay. V times I. When this is high, V becomes low. When you have too much reactive power, the voltage now becomes low. Too much reactive power. Now this is not the generator. This is the load. Okay, this is the load of the car. Now you need to push more for the car, the same speed. So this is too much reactive power, not from the generator. This is from the load. Okay, from the load needs this reactive power. So when we draw, this is the load, and this is also the load. So this becomes too much. Okay, becomes too much for the load. Heavy becomes heavy if you pull it up like this. So that's why it's straight. You pull it straight. All right. So this is so when there is not enough reactive power to support the inductive loads, there is not enough. The voltage sags, so the voltage drops when there is not enough reactive power, and then it's not possible to deliver the required power. Required power, why? When the voltage is down, VI cosine theta. VI cosine theta, voltage is down, therefore the real power also will be down. So we cannot supply real power. Okay. So the reactive power plays a very important role in delivering the power itself. We want to deliver real power and also reactive power if there are motors. If there is industry, heavy industry needs reactive power. So we need to deliver real power and reactive power, but not too much reactive power. So we need external support for reactive power for the industry. This external support can come from the synchronous condenser or from capacitors, bank of capacitors. Installed in the industry, they are installed close to the industry, to the factory. Okay. and then we can deliver the necessary, and the voltage becomes the nominal voltage, the voltage which is required. For example, 0.95 per unit, okay, 95%, and so on. Or 100% is optimal, of course. So we want all our voltages to be 100%. What do we mean by 100%? 132 kilovolt. So we want the bus to be 132 kilovolt. Okay, all buses to be 132 kilovolt. Okay, so that's we're already now example power factor correction. That's what we're talking about. We need some. This is VA. This is S. Now 100 kVA S. A load with a power factor 0.8 lagging. So this is the statement. So know exactly the statement of the problem. So when they say power factor 0.8 lagging, it means the load is Rx load. So R and X, inductive load. This is an inductive load, 0.8 lagging. If it is 0.8 leading, it's a capacitive load. Too much reactive power leading, too much reactive power. Here, it absorbs reactive power. The load absorbs reactive power. Lagging, 0.8 lagging. And we would like to correct the power factor to 0.95. Now we know, understand why we need to always correct the reactive power, the power factor. Because of this, as you can see, okay, because of this part here, it becomes heavy now to deliver. So we always want to react. What do we mean by we want to improve the reactive power? Means that we want this to be less. This is the idea. Okay, we want this vertical line here to be less, so it is smooth to pull the car. Smooth to pull the car. So we want to reduce this one. That's where we say that we want to improve the reactive power. So therefore, the angle needs here to be reduced. This angle here to be reduced. Okay, so this is the idea. All right. Okay, so therefore now, okay, we'd like to correct the power factor to 0.95. And now, as an engineer, you understand we need to correct this reactive power because it will be heavy. Okay, as we mentioned, that will be heavy for the load to deliver the real power. So we need to improve the reactive power to 0.95. What does it mean? It means that we reduce the angle. Okay. So there now what we have in here. So this is 0.95. We already have it in here. So we determine the angle. What angle here? This is the angle 36.9, which is the angle that we talk about, which is like this. This angle. So we want to reduce this part down. We want to reduce it. If this is 1, if we want to reduce to 1, it means that we don't want a reactive power. We want to support all the reactive power from the capacitor. If we want it 1, but we want it 0.95. Now, by the way, you say now 0.95, 0.96, 0.99, and then 1. And then we don't have 1.1. We have what? 0.99 leading, becomes leading. Okay, so remember these. So the maximum power factor is 1. Okay, so 0.95, 0.96, 0.97, 0.98, 0.99, and then 1, and then becomes 0.99, but it becomes leading instead of lagging. So it becomes leading power factor. So we never have power factor is 1. So please, now I take you as an engineer, makes sense. So if you write, for example, 1.1, for example, you calculate it in the exam or quiz or homework, and then you write 1.1 power factor is 1.1. Your calculator gives you 1.1 because you made a mistake somewhere. And you wrote 1.1. It gives me that you don't know what is going on. You're just plugging in the numbers here because these are simple things. It's easy, it's straightforward. You can determine the R, the P, the Q, etc. But to make sense now, we don't have 1.1. That means you don't know what is going on in the power. Okay. So too much reactive power, it means this angle here, we brought it down to 0 angle, which is 1, and then increase the angle, means it's also going down. Therefore, now S becomes here like this. So becomes leading reactive power, becomes leading power, reactive power, because we just increase decrease the angle. We decrease the angle, we do bring it down until it becomes here also, down. Then this angle here becomes on this part here. So therefore becomes leading power factor. All right, so what's the idea here? The idea is to find, what do we want to find, first of all? Now this is a lagging power factor, 0.8, and this is S. When you see this, we want to improve power factor, it means we want to play with the reactive power. What do we want to do? We want to decrease reactive power. Therefore, it comes to your mind that I want to see what is the current reactive power now. This is the current reactive power from S. How do I find this one? We already discussed this one, okay, with the sine angle. VI sine theta. So we want to find theta. And then find cosine inverse of 0.8, give you the angle. This is the angle now. Then sine this angle times voltage or times S. S sine theta will give you the reactive power. Muhammad Fahad Al-Hariri, you are late. You are late, ya Muhammad. So you will be absent for this course. Yes, so you will be absent, ya Muhammad Fahad, for this. So don't tell me that you were there, please. Okay, you were okay. But anyhow, okay. Thank you, Muhammad. Wallahi, you give me okay. But inshallah, I encourage you to listen to or to watch this lecture here after the lecture. All the lectures are recorded. All our lectures are recorded, so you can watch them. Okay. And to remove, sometimes I need to remove maybe your absent if you have a case. To remove your absent here, I need to ask you some questions that you listen to the lecture or not. And this is for limited cases. Okay. So we don't want to make it a school that you are here or you're not there. And we prepare you as engineers, so we trust you. So we give you this responsibility to attend these classes. Otherwise, if not, then you need to read or to watch the videos. Okay, take notes, and then I ask you about a number of things here. Okay, so the question here, how can I find the records? We can discuss this inshallah later. Okay, and on the blackboard. So we will see this inshallah just after the class. Remind me to show you where we can you see the recordings in the blackboard. All right. Okay, so now what's the idea here? Well, the idea here is we want to play with the reactive power. So we want to find what is the current reactive power. So this is the current reactive power, J60 kilovolt ampere. No, J60 kilovar. This kVA is for the S. Kilovolt ampere is for the S. So this is megawatt, and this is, or kilowatt, and this is kilovar. If you add these two, and you know how to add a complex number, okay, you add them as complex numbers, then you will get S, you will get this 100. So 80 plus J60, if we add them magnitude, we get 100. All right, so we want to play with this one. So what is this actually? This is the power factor is 36.9 with this 0.8 lagging. Okay. Now we want to improve to 0.95. To improve it to 0.95, we want to reduce this. To how much to reduce? To 0.95. So we want to reduce cosine inverse of 0.95. Will give you 18. It means that we want to reduce the 36.9 to 18.2 degree. 18.2 degree. Okay, so we want to make it 18.2 degree. So we want to make it small. Okay, we wanted to make it here. This one. It was here. So we want to bring it down. So therefore now we know the difference, so we can have it. We want to bring it here. So what we do here, S new, the new now, the new what? The new, this new here. What will be the new here if we want to find it? So I would like to protect, okay, to correct this. So this is the 80, we did not touch, always put the same thing here. The real power is the same, the red one here, as you can see, the horizontal one. We did not touch it. We only play with the reactive power on the compensation. All right. So 80 plus J60 minus the capacitor. This comes from the capacitor, reactive power. So how much capacitor we need to do? 60 minus the capacitor will give you 10 and 18.2. So this will be 26.3 kilobar. So you just take okay, 26.3 kilobar. 60 minus Q cap. Q cap. Q cap means the reactive power of the capacitor that we want to add it. So we just, there are so many things you can do, so many methods you can do it, so many ways you can do this one. The idea, I want to reduce this angle here to what? To 18.2. Therefore, this reactive power now, the new reactive power is this part. This is now the new reactive power. That's the idea. Okay. So how much capacitor I need? I need this much capacitor, 33.7. Where is this capacitor here? Is this part here? This part. So I want to take out this part here from the generation, from the generators, and put it in the load. So I need to put a capacitor close to the load. Close to the load, it means that it is in the factory itself, in the industry itself. So when you visit aluminum, for example, aluminum or steel or any big companies here, you will find a substation. They have their own power substation, and they have the capacitor banks. The capacitor banks, they supply their own capacitors, and they take only very little reactive power. I mean, they supply their own reactive power. They only take a little reactive power from the system, from Kahraman. Only small reactive power they take. The most of the reactive power must be supplied. So that's what we mean by this compensation. Yes.
Doctor, shouldn't the capacitive reactive power be negative? So negative 33.7.
Okay. No, not this. What it means here? Not negative. This is what is produced from the capacitor. Produced, so it's positive. So the capacitor must supply 33.7 kilobar. This is what it means. So the capacitor must supply, must give 33.7 kilovar, which is this part here. This part here, we want to get rid of this. Okay. So the capacitor does not absorb reactive power. So it depends on the convention that you use. So we use here delivering capacitor must deliver 33.7 kilowatt. So we put it positive. If you are confused, positive, negative, in the homeworks or exams, etc., you can say the capacitor delivers 33.7 kilowatt. That's it. So you don't put positive or negative. That confuses you.
Okay, so 33.7 we can put between brackets supply.
From the capacitor.
Yes. Oh, okay.
From the capacitor. So how much will be then? 33.7. How much will be from the load? How much will be from the generator?
It will be 60 minus 33.7.
Yes, which is this part.
Doctor, it will be negative if the power factor was leading, عفوا, right? The Q capacitor, the 33.7 kilowatt, it will be negative if the power factor is leading.
If the power factor is leading, it will be negative. And I don't know whether you will write it negative or positive. If the power factor is leading, the capacitor, so the capacitor will not absorb reactive power. The capacitor gives reactive power. The capacitor always gives reactive power. So the power factor will be leading, but it will not be here negative. Leading means that the generator will not supply this. This here, if too much reactive power, if this is too much, more than 60, for example, this will be what? This will be negative. So the number here, this will be negative. It means the generator is absorbing reactive power. If this is too much, that's what we're talking. That's why we mentioned that the capacitor, you put too much capacitor. So this will be negative, correct? Too much capacitor. So the more than 60 here, it will be negative, correct? If this is negative, what does it mean? It means the generator is absorbing reactive power. The capacitor is still producing reactive power, but the generator is absorbing reactive power. The generator at the sending end is absorbing reactive power because it's too much capacity. Okay, too much reactive power on the system. It must be absorbed from somewhere. Okay, absorbed from the if it's too much, then the generator, they close the generator, they shut it down. They cannot, there's a limit for absorption. Shut it down. Too much is not good. Too little is not good. It must supply nominal. It must be close to 0.95 to 1 per unit. Okay, that's okay. Good. Okay, too much is not good. Too little is not good. Okay. So that is, now we need 33.7 kilowatt from the capacitor for the generator to produce this kilowatt. The generator will produce 26.3 kilowatt from the generator and 23, so this will be 34 and 26.3 from the system, from the generator, and 33.7 kilowatt from the capacitor. If you add them, you will get the 60, which is this part here. You see now, the load is the same. 100 kilovolt ampere is the same. We did not change the 100 kilovolt ampere. Okay, so if you add 26.3 plus 33.7 will give you this. At the beginning, this becomes 60. From the beginning, we did not change the load. The load, we have no control on the load. People are using the electricity. They have the load. They do not have control on the load, but we can control the reactive power to supply the customer. So instead of giving of 60 kilo instead of 60 kilovar comes from the generator. We want to help the generator, to relieve the generator instead of having 60 kilovar. You see, how do we know? We usually, the system here runs about 10% or 20% from the real power. If this is 80, we want to bring it maybe to low, maybe 20%. Okay, 20%. So this will be about 20 or 18 or something. Okay, about 18, 20% of the real power and small. We cannot have very large reactive power close to the real power. This is too much just by looking at the numbers. Too much reactive power. In theory, when we calculate it, we can calculate like this. You don't worry about it. But in system reality, this is too much. Why? Because it's not. It's about we're looking for 20% of reactive power. Now we're talking about the load now, not the load. But we have to supply this. From where we supply this? This part here, real power will be supplied from the generator, from Ras Laffan, Ras Laffan, okay, and so on. This reactive power, we can't control it now. We decide where do we want to supply it. We ask all the industry to supply the reactive power. We will not supply you any reactive power. So the industry must put capacitors, not only 33.7, they must supply this 60. They must put 60 kilovar. If you put 60 kilovar, the power factor becomes 1. Power factor becomes 1. Why? Because no reactive power comes from the system. All the reactive power which is needed in the industry is supplied also by their own industry. Okay, they supplied by the industry. So the system does not see any reactive power. So the power factor becomes 1. But the power factor is not 1 in this case. The power factor is 0.95. What does it mean? It means that there are some reactive power will come from the generator, from Ras Laffan or Ras Laffan, from the generating stations. Some reactive power. How much reactive power will come from the generator? This much. It's 26.3. Will come from where? From the generating stations. And what about the rest? What about this? We need 60 for the load. The other, this 60 comes from the capacitor that you installed capacitor, because this from the compensation you installed capacitor in the load. So if you add them, you will get 60. So again, this part here, we do not change it. This part here, we must satisfy the load. Okay, so we still have 80 real power, and the rest here comes part from the capacitor. All right, so this is clear, inshallah, for you. And when you do the system there and you look at the system that will be explained by Sujoy, the power flow program, when you look at it, you need, as an engineer, you need to look at the data. This is okay, not okay. Okay, if you're asking, for example, the load, if we give you sometimes we give you, you generate the question itself. You generate how many, you generate a system. If I ask you, design a system that maybe have 9 buses. Now you understand 9 buses, okay, or maybe 30 buses. And then also you specify the load. You will not specify the load 80 megavar and 80 kilowatt and 60 kilowatt, all from the generator. This is too much. Okay, you need to make it. This is low, so you want to reduce this part here. And then, but it's okay. They can have it like this, but it should come from somewhere, from the capacitors. Okay, here to the load. All right, so we talked not too much. How the capacitor looks like? The capacitor looks like this, as you can see. They put it like this. Nice, neat, a panel. This is a capacitors, and they call it capacitor bank. Capacitor bank. It also could be like this, what you see here, distribution capacitors. They put it here on the way while they are going there. Okay, where you will find these? You will find these in the industry, in the factory. If you go to the factories, they have the room and must be cooled down. So this is cool. But it's just a capacitor. There's nothing moving in this one. no movement, just a black, we call it a capacitor bank. We call it a capacitor bank. There could be so many, by the way, not necessarily only these, but it could be so many. Okay, depends how much capacitor we need, and we can control this. How many this time we need the 60 kilowatt the whole together. Then we take the whole thing. Okay, we take the whole thing here. For example, we want only half. We want only to supply 30 megawatt, so we only take one part of it, for example. Okay, so we can control the capacitors, how much reactive power we need. Okay. But if it's fixed capacitor, then that's it. So it's fixed, we call it fixed capacitor, then always we supply this reactive power, fixed capacitor. Another reactive power compensator is the condensers. Okay, so now this is we exceeded the time, so I will leave you here now. But anyhow, this is the condenser. Just I need to finish this, please, with me. Network. This is already familiar with the network equations. Nodal analysis. Please review these in your textbook, chapter 2, section 2. We will not explain it here. Okay, this is in the circuit that you had, circuit 1, even circuit 1, nodal analysis. So network, but instead of node, we call it a bus. It doesn't matter. But nodal analysis, and then it goes on. So we need to discuss this, inshallah, next lecture. Okay, I will stop the recorder here.